Hey there, YouTubers! Pardon the lawnmower noises. Hi there, Dr. Sheep here. Welcome back to another physics video in a park. Last time we did this was, I think the last time we did a spin video, or maybe quantum mechanics. It's quantum mechanics, definitely. Point is, today we are talking about spin, which is why I'm on my favorite piece of playground equipment, which is weird to say as a 22-year-old. Nevertheless, that is the merry-go-round. More on that later. We're looking for the most literal definition of spin. One will look to the dictionary. And according to Google, the most basic verb definition of spin is to turn or to cause to turn. Now, there are many definitions after that. My favorite is a verb definition labeled as the physics meaning, and that is, if I look at my piece of paper here, the intrinsic angular momentum of a subatomic particle. That's not the physics definition I would give. It's probably the one Phil would give, but nevertheless, there it is. Now, the spin of subatomic particles is interesting and all, but that's another video for another day. You know, it's actually warmer in the lab than it was outside yesterday when I recorded the beginning of this video, which is very interesting to say the least. Anyways, why do I find spinning objects interesting enough that I have made multiple videos about them and will probably make more videos in the future? Well, it's all about centripetal acceleration and what we can do with it. So what is centripetal acceleration? Well, let's break it down into two parts. First, we have centripetal, which means moving or tending to move towards a center. This part kind of always confused me, and to be honest, it still does, but the more I thought about it, the more I looked at it, the more clear it became. Let's say you have a ball at the end of a string. As you start to spin it, you can feel the ball wanting to leave in a direction that is tangent to the circle. The ball wants to go in this direction, but is held back by the string. The ball, therefore, is being constantly pulled back towards the center by the string, thus centripetal. So what does acceleration mean? Acceleration is defined by a change in velocity over a change in time. A good example of this is when you're in a parked car. What? Let me finish. You are not moving, but when the driver hits the accelerator, you feel as if you're being pushed back into your seat. This is because the car is going from a state of zero to something higher than zero over a period of time. Your inertia wants to keep you in place. That's Newton's first law. But the car wants to push you along. You feel this until the car reaches a constant velocity, meaning the car is done accelerating. This doesn't make a lot of sense, though, when in relation to the ball at the end of the string. The ball is moving at a constant speed. How can it be accelerating? What you have to remember is that velocity and speed are different. Velocity is a vector, meaning it has two components, direction and magnitude.
Vector! That's me, because I'm committing crimes with both direction and magnitude. Oh yeah!
Magnitude is speed, and direction is the course along which the speed is acting on. What this means is that you have an acceleration without a change in speed. The direction of your speed can constantly be changing, allowing for acceleration to happen. After combining both these concepts, I feel as if your mind is beginning to open up, and you may realize how much stuff spins and the kinds of forces at play here. Now, the thought experiment I'm going to propose is quite possibly the definition of supersized. This is okay because it's just a thought experiment, and honestly, it's extremely relatable because I feel like most of us have thought of this at least once in our life. I will do an actual supersized experiment later, but for now, let's think about the Earth. The Earth is big and round and is spinning on its axis, despite what flat earthers want you to think. Now, the Earth's velocity as it spins on its axis is about 1,000 miles per hour. Now, this is a science show, so we need something that isn't in freedom units, and we want something more precise, and we want it to be in meters per second. So that is 460 meters per second. That is the speed of the Earth's spinning on its axis. Now we need the radius, which we can find using the circumference, which is 40,075,000 meters. And yes, we're going to calculate the radius using the circumference because I'm too lazy to find another source that has the radius, yet somehow doing the calculations is being lazy? What? Don't ask me, I don't understand where it came from, but we can calculate radius by taking the circumference and dividing it by 2 pi. Formula for circumference is 2 pi r. Or pi times the diameter if you really want to go that way. So after doing this, we get the radius of the Earth, which is 6,381,369 giggity meters. Yes, I don't give a damn about sig figs, if you're wondering. Using this information, we can find the centripetal acceleration due to the Earth spinning at its equator. May I point that out? And that formula is velocity divided by the radius. Sorry, is velocity squared divided by the radius. So, we take 460, square that, and divide it by our radius, and we get, drumroll please, you can already see it, 0.03 meters per second squared, which I think is smaller than what I got last time I did this calculation, but that could be a variety of things, you know, the amount of digits I kept in the calculations, the rounding, to how I got my radius, to me just not caring. Nevertheless, I think it's time to work with some smaller numbers. Pardon me for not having a teleprompter and not having this memorized. I don't have that kind of time, and I'm in a park. Nevertheless, though, we have the script here. This is my favorite merry-go-round in the entire world, because I have a lot of memories on this thing. It's in one of my favorite towns, and it means a lot to me. Nevertheless, though, it has a radius of about 1.5 meters. That isn't an actual calculation. I didn't bring a tape measure with me. I wasn't going to rewrite the script and do all the recalculations. 1.5 makes things easy. Anyway, let's solve things backwards from the previous equation. How fast do I need to get this thing to spin to pull 1g? 1g is the acceleration due to the Earth's gravity. This is the opposite of what we calculated earlier. As the Earth was trying to throw you off in the previous problem, this is trying to pull you closer. The acceleration due to the Earth's gravity is 9.8 meters per second squared. To find a velocity, we will multiply 9.8 by the radius, then find the square root of this answer. This gets us 14.7 meters per second. This doesn't do us a lot of good because it feels very abstract. Yes, I don't use the metric system, but even if I did, I would know kilometers per hour, not meters per second. And kilometers per hour doesn't exactly work on this scale. So we need something that's more fitting to this and more tangible. That's where we get something called revolutions per second. This is how many rotations an object can make in a given time frame. In this case, it's a second. This can be calculated by taking the velocity and dividing it by the circumference. As I mentioned earlier, the circumference is 2 times pi times the radius, or pi times the diameter. Our circumference is 9.42 meters. This means that I need to spin this merry-go-round at 1.56 revolutions per second. I'm gonna need a pretty big dude to pull that off. But anyways, now it's time for my favorite part of these videos. Now it's time to supersize. Now it's time to supersize. This is a full cloverleaf interchange. It gets that name because if you look at it from the air, you'll see 4 loops that it forms. Now, getting a radius of this thing was a bit of a challenge, but with a little help from my friend Google Maps, I got the tightest radius about 54 meters. Now, the next question is, how fast do I need to go in my truck for 1g of acceleration in the horizontal axis? Well, let's calculate that, shall we? So we take 9.8 times 54 hour to get 529.2. You take the square root of that to get 23 meters per second. That's 82 kilometers per hour or 51.4 miles per hour. Now, if you ever drive with something like this at those speeds, you're gonna feel like you want to die. And I don't need to tell you this, but I'm gonna tell you anyways, don't try it. I don't need to see the news where some kid tried to pull 1G on a 4E full clover, whatever you want to call it. Thank you, Phil. And they flew off and maimed themselves. So don't do it. Please. That's it. That's all you need to pull 1G, about 50 miles per hour. Do we want to try it? Pulling 1G, let's go, baby!
All right, now gun it.
I can't. We're
What are we doing?
35.
Yeah, no,
You got. I mean, maybe not in my truck, but in your car, maybe I'd be willing to pull more. But so, what can we conclude from today's video? Well, I won't touch torque with a 10-foot pull because that would be a lot of torque. In the meantime, I'd like to thank you all for watching. Please like, comment, share, and subscribe. New science videos every other Friday, 11 a.m. Central Time. New podcasts every other Friday, 11 a.m. Central Time. And good night. Wow, that was like a physics dad joke. What? Really, that's a physics dad joke. Wow. All right. I didn't even realize to put that in there. Because that's a lot. Because it'd be a lot of torque. Oh my god! I didn't realize. God, it's warm in here. Note to future me editing. Remember to interject the what after I say parked car, which is a constant velocity. You're in your. My god! I keep looking all around. Take 3. What you have to remember is that velocity. Oh shoot! Did I say velocity or speed? Motherfucker. Take 4. Direction and magnitude. Oh no! What am I doing with my life? You can have an acceleration without a motherfucker. Why can't I read this now? Take 2. Me. Gets a drink to make my voice feel better. Also me. Drink makes voice feel worse. Who knew, right? That's 82 nothing. Get off. We're gonna get hit and die. I was gonna laugh when we got hit by a golf cart. It's gonna be a good time. Subs for trees. Subs for trees. Subs for trees. Subs for trees. Oh, you're still here? I thought I told you to go home. Oh, you want more? I'm flattered. Check out the playlist. If you want exclusive content, check out my Instagram, Dr_sheep_YouTube. That's all lowercase. If you want to help the earth, subscribe. When I reach 100 subscribers, I'm going to plant 10 trees. If you feel that's too small, then check out my channel chart where I lay out even bigger goals. Finally, stick around for the next 20 seconds to give me that sweet watch time. Bye.